I'm the Deputy Secretary for ECSA. So today we've got a talk from Craig Smeaton, but just a little bit of housekeeping to begin with. So while we're doing the presentation, please can you make sure that you're muted and that your cameras are off as well, just to avoid any interference. So I'm going to introduce our talker for today. So Craig is a lecturer from the School of Geography and Sustainable Development at the University of St Andrews. His research is broadly focused on developing a better understanding of the processes which govern the accumulation and storage of carbon in coastal and marine sedimentary environments. And his recent work has included the quantification of organic carbon accumulating and stored in UK salt marshes and the development of an organic matter reactivity index using thermal decomposition approaches. So over to you, Craig. And if anyone's got any questions, either pop them in the chat or wait till the end of the presentation.
Okay, thanks for the intro. So just wait until this works.
Yeah.
Great. So yeah, I'm going to talk about fjords as hotspots for carbon storage and burial. So most of this work is from my PhD and half of my postdoc and some ongoing work. So this was broadly funded by NERC and the Scottish Blue Carbon Forum, which is semi-defunct at the moment, but they gave me plenty of money to do some of this. So fjords, Scotland has got them. They're called sea locks, and this is the Loch Etive, just north of Oban, where I did a lot of my PhD work. So just in case you don't know, what is a fjord? So a fjord is an over-deeping glacial valley that's connected to the marine environment. It comes in two broad flavours of glaciated, which is in its name. There's a glacier still at the end of it, and it's a completely different system to an unglaciated fjord that we have here, southern Norway, New Zealand, Sweden. And then there's one in the middle that the glacier is not directly pumping stuff into the fjord, but is in the upper catchment and influences it. From this map, you can see the majority of fjords are in the northern hemisphere. We can guess where most of them are. Norway, Iceland, Greenland, Canada, some weird Russian islands. And then in the southern hemisphere, it's basically Chile and New Zealand. So why do I care, or why should we care about fjords? So in 2015, there was a paper written about them as global hotspots of carbon burial, which really annoyed me since I started my PhD in 2014 and they consulted me. But this paper found that across the sampled fjords anyway, the carbon burial rate was really high. And when compared to other sediments across the planet, the area normalized value is orders of magnitude bigger. So non-deltaic and deltaic sediments are shelf sediments. So there's obviously more carbon stored there, but fjords cover a far smaller area. So when you normalize for area, fjords are a hotspot, the sedimentary hotspot for carbon burial. This paper came out with a number that fjords account for 11% of annual marine carbon burial, which is a really nice number for funded applications. But how this fits into reality is a different question. So in this paper, they assumed all fjords were full of mud, and they had very high burial rates from New Zealand that they applied across the globe. And in reality, neither of those things were a particularly good idea, but they got a Nature Geo paper, so good on them. So what I'm going to talk about is how my PhD developed, how my postdoc went, and what I'm currently working on. So the big questions in the area are how much carbon is stored in these sediments, how is the carbon distributed, at what rate is the carbon buried, what's the source and the reactivity of the carbon, how old is it fresh carbon, is it old carbon, and generally how have these developed through time. So most of this work will focus on the Scottish fjords or sea locks. So we have around 111 what I would consider fjords, large inlets with sills. So the geomorphology, there's at least one sill that restricts flow into these systems. So this was the focus of most of my work in the early days of my PhD and postdoc. So we'll go through a couple of these questions and how we answer them and what questions were made. So how much carbon is stored? So the very first thing, the big question, how much is there? So prior to my PhD, there was a seismic survey that you can see in the bottom diagram of the tracks of this survey. So it ended up covering most of Loch Sunart, which is again just above Oban. So we got seismic geophysics for this whole area. Then we also had long gravity cores that got all the way into the glacial material. So we worked these up. We took the gravity cores, took samples, measured carbon, bulk density, physical properties, and then we tried to tie this into the geophysics. So this is a normal, a fairly standard geophysical, seismic geophysical profile of the sediment of Loch Sunart. So it could be broken up into four packages. So the orange is glacial material dumped at the end of the when the glaciers were retreating up the catchment. So this is carbon poor, coarse material. The green layer is younger, driest material. So we only find this in the inner basin. So this is material that was deposited during the glacial readvancement of the younger, driest period. And then the two blue layers are basically Holocene, the last 11,500 years-ish of sediment accumulation. So in the deepest part, some of these sediment packages total about 70 to 100 meters. In the shallowest parts, we got through all of them or into the glacial material with a 6-meter core. So we had all that. We had all these tracks. We built a 3D model using all these of the different layers, and then basically calculated the volume of sediment in between those different layers. Combined this with the bulk density and carbon data, and we managed to calculate a stock. So it was all well and good getting a stock for one fjord, but how do we go from one fjord to all of them? So the good thing is there was 5 other fjords with this level of seismics, which is really unusual. So Loch Etive, Loch Broom, Little Loch Broom up in near Ullapool, and Loch Crieran, which is again just above Oban. These were the exact same process was undertaken on these. We got carbon stocks for all of them, and then we tried to work out similarities between those fjords and the other 112. So we did a cluster analysis of as much data as we could pull out. So handily, in the 80s, someone had a bit too much time on their hands. It came up with a CLOC catalogue with all data on all the parameters of these fjords. We threw that into a cluster analysis, and it threw out 4 clusters. So group 1, the orange, is what we are calling the standard fjord. It is the standard issue fjord that we would expect around the world. Multiple sills, deep, and these are almost exclusively found on the mainland, except for a few on the eastern edge of Skye. The green group is, again, they are what we class fjords, but they are more distal to the centre of the ice flow, basically, during the Holocene. Group 3 is very shallow systems, so we find these in Shetland and the Outer Hebrides, and in honesty, these are not fjords. These are what the Norwegians and Swedes would call fjords. They're basically drowned estuaries, which are, they've got no sills, they're quite flat bottomed. And then group 4 is the oddities, which is the 2 that fell out here were Loch Linnhe, which is actually just it's a giant loch or giant fjord that's more a channel than a fjord, so that the sills don't really seal it up as much, and locative, which is quite a strange system. With the upper basin is permanently hypoxic with low oxygen. The bottom system is a more general, normal fjord, but the main input into that is through lock awe, so there's a giant freshwater lock that feeds that, so it's got a pre-sediment trap, so not much sediment gets to it, and there's a hydroelectric dam in between, so it's a really odd one. But the good news was the 5 systems we had, 2 fell into group 1, 2 fell into group 2, and 1 fell into group 4. And as we didn't really consider group 3 to be real fjords, that didn't really matter. We never had an analog. So we used those numbers and upscaled to get a really rough first order estimate. So what we figured out for the Scottish fjords was the post-glacial sediments hold about 252 million tonnes of organic carbon, while the glacial sediments hold about 43 million tonnes. And the inorganic carbon, the opposite end, there's 214 million tonnes of in the post-glacial sediment, and there's 130 million tonnes of inorganic carbon in the glacial sediment. And that's not a massive surprise. They're pulling, when those glaciers dump stuff, they've been scraping continents for thousands of years. They picked stuff up on the ocean bed and dumped it. So it's a real mix of stuff. And so overall, the organic carbon is what we really want to know about climate. So 252 million tonnes. So that was a really rough, how much is there to get a broad starting point to, is it worth looking at? And the answer was yes. So what we really want to dig into is the spatial distribution of the carbon. But how do we do this? We're never going to go out and collect enough samples or geophysics to fully map these. So we had to come up with a way of using old data, new data that's becoming available, and how do we combine them? So we came across basically 3 kinds of, or 2 kinds of data as 3 approaches. So the tier 1 legacy data, there's a pile of grab sample data that's been reported over the years and sediment types been reported. These are ecological surveys by divers that have to report what kind of sediment it is. And then there's anchoring details from the UKHO. So on all marine maps, there is what is the type of sediment. So when your boat puts down its anchor, it won't float away. So we took all of this and basically did a simple spatial extrapolation and managed to create the tier 1 map of all of Scotland. The tier 2 map, we used backscatter data. So this is generally a byproduct of multi-beam bathymetry. So backscatter works by, it basically tells you how hard the return signal is. And obviously the soft stuff is mud, the hard stuff is rock, and then you can calibrate in between. So we did this for as many sites as we had data, but this is fairly limited to the bigger fjords and the ones around the Clyde and Oban. The problem with this is it doesn't get into the really close coastal areas because the ship or the boat cannot get in there with the equipment. So there's always this white ribbon. And then the tier 3 approach was to basically combine this and use the legacy data to fill in the gaps where the backscatter couldn't. Then we did a confidence map, and you basically see the confidence. We've got high confidence where we've got backscatter, and we've got a lot lower confidence where it's just the legacy data. So we did this, and then we combined it with data surface samples we collected. So over the years, we collected about 356 surface samples from across the main folk sediment types, measured the carbon and bulk density, and then basically applied these ranges to the mapped sediment type. And you can see this is Loch Linnhe, Etive, and Creerin, and Oban is just in the south there. And you can see that the spatial diversity of the carbon content is very different across the fjord. What we found from this is about 40 to 60% of fjord sediments are muddy, and the other 40-ish, 30, 40% is coarse. So if we go back to that number at the very start, where they calculate all fjords globally to be full of mud, that number might be as little as 30% off, or could be way higher in certain environments. So we need to think about trying to do this at a greater scale, at a global scale, to figure out what these numbers really are. And when we did this, so since we only had surface samples, we only calculated the stock to 10 centimeters, and for all the systems, we got 416 million tons of organic carbon in the top 10 centimeters. So we come to OC burial. So Scotland was lacking this for a very long time. We had surface data, but we had no organic carbon burial data. So how do we fix this? So we think, okay, globally there's 18 million tons is buried a year. That was that Smith paper at the start, which I think is not correct. And then the same group a year later upped this to 21 to 31 million tons per year, which they in the paper say is a likely an underestimation. In my opinion, this is a massive overestimation, and they never really engaged with the problem of the first estimates. So we want to sort of fix this. So in 2018, we got a nice little cruise with Marine Scotland, where we basically did a loop of the country and sampled all these fjords, took multi-cores, and had a crack at working out the accumulation rate. So what we did, this is the multi-core, basically a big heavy bit of metal with some plastic tubes. We pull this out. We've got technically undisturbed samples, but you can see from there, undisturbed is questionable. And we can work out accumulation rates using radionuclides. So we used lead-210, cesium, and americium dating to get profiles, and we measured organic carbon down the profile. So in this plot, the organic carbon accumulation rate is the black lines, and the terrestrial organic carbon is the orange. So focusing on the black line. And you can see across the fjords, they differ quite significantly. And there's been some quite clear shifts over the last 150 years of carbon input. And when you get the averages across these systems, this is what we find. So the average accumulation rate is basically around 40 grams per meter square per year, but we've got some high outliers with up to 111. But most around between the 40 and 60 mark. And the previous global average was that blue line, which would suggest all of a sudden our samples are mostly above it, which we thought, all right, we must have done something wrong. The Scottish system should be accumulating more than New Zealand systems. There should be a lot more soil going into those. What have we done wrong? And what we think it is we've got a larger marine input into these systems, which increases the OC accumulation rate. And in combination with the terrestrial, we get these slightly higher rates. In all honesty, the more data that comes out, the more that global average is going toward it. So yeah, like I say, the global average is 57.1, or our average across Scotland is 57.1. It ranges between 34 to 111 grams. And overall, the Scottish fjords bury 84,000 tons of carbon a year. This is broadly, so 84,000 tons. It doesn't sound like much, but this is equivalent to 10% of the organic carbon accumulation in the North Sea. And the North Sea is 190 times bigger than the fjords. So it's a big chunk of carbon accumulation in Scotland, or the UK, if we're being honest. So that was that. So we got a number. So we know how much is being buried, we know how much is stored overall. And one of the other big questions is, where does this carbon come from? So obviously, fjords are on the coast. They're directly coupled to catchments. There's going to be a large input of terrestrial carbon. So globally, it's estimated that between 52 and 66% of the carbon in fjord sediments is terrestrial. The issue with these estimates, it was estimated using New Zealand fjords, which are hypoxic and basically almost completely restricted from marine input. So we had to work out what was going on in the UK. So with another cruise, we got around all the way around Scotland this time and collected surface samples and transects down all these fjords. So in total, we ended up with a lot of samples. We went out and measured organic carbon as standard, delta 13C, so isotopes, and we also got the NC ratio. And these can help work out the source of the carbon, marine or terrestrial. So we put this through binary mixing models and Bayesian mixing models to get an idea of the percentage terrestrial input. And what we get is basically the bottom of this panel is fraction terrestrial. So a lot of it is floating around the 40% of the carbon's terrestrial mark, with some up to some in the hypoxic basins and the really constricted ones almost being 100%. So we got numbers for all these fjords. But again, this is not every fjord in Scotland. So how do we work out, how do we at least estimate how much is terrestrial input is in other fjords? So Joe Faust and Jochen Nies in 2019 came up with this conceptual model to work out, or to at least explain why we see more marine and more terrestrial different fjord systems. And it basically comes down to the freshwater input and the size of the sill and the seawater input. So for example, in A, there's low marine input, low freshwater input. So in general, there's going to be less OM ter. But in one where there's high in both, it's equal, and one where there's high freshwater input and low marine, there's more terrestrial material. So that's the way to think about it. So we took that idea, that concept, and said, how can we use this conceptual idea to model terrestrial input? So we tried a pile of possible variables, but what we ended up going for was tidal range times outer sill depth was a good predictor for the fraction of terrestrial carbon found in the system. So when we included all mainland fjords, so every fjord we had, every data point we had, we got an R squared of 0.59, which is okay. But when we took out the fjords where we had less than 5 samples and just focused on the big data sets, we got a much better relationship. So we applied this relationship to all the fjords, and it allowed us to model basically how much for terrestrial carbon would be there. So in the measured sites, we found 47 plus or minus 12%. In the modelled sites, we got 52 plus or minus 10. And that global number comes back. It's globally it's estimated that 52 to 66% of the carbon in fjord sediments is terrestrial. So our numbers fit bang in there. It matched up quite well. But when you actually plot them against individual countries and don't take the average from that paper, it's a slightly different story, because from these global averages or national averages, I don't really see how that paper got the average of 52 to 66%. And you can see there's quite a big spread in all this data. So in reality, globally, is between about 30 and 80% of the carbon is terrestrial. Just depends on where you sample. Sample at the marine end, it's going to be more marine. Sample at the head, it's going to be more terrestrial. But with this, we got a decent idea of the terrestrial carbon input. So with that, we have the burial rates, the storage, and the general source of the carbon in the fjord. So what do we need to try and finish this budget and how to basically round it off, work out the inputs, outputs? So we really need the terrestrial input. So this is a fairly, I don't want to say conceptual but this is a fairly rough way we came up of doing it. So we took the Scottish soil map, the European soil loss model, and combined them. So this is soil loss due to water, so basically rainfall and how much of this is washed off. Then we could create a soil loss rate map for all the catchments of the fjords, and then we worked out, okay, this is how much organic carbon annually is mobilized. So the mean across the mean amount is 5.06 million tons. It's anywhere between 4.3 and 5.78. But this is the important thing we have to think about is that's what's mobilized in the catchment. It's not necessarily what gets to the fjord. So there's a paper from the 80s that basically says 10% of all the of carbon mobilized in a catchment reaches the fjord. So we used that number to go, basically it's around 500,000 tons each year is entering the system, which is a lot. When you think the last number was Fjords burning 87,000 tons, so it's technically 5 times the amount of organic carbon coming in. So when we do these calculations, the organic carbon, the terrestrial organic carbon accumulation rate is about 51,000 tons per year in these fjords, which represents about 7.2 and 10.2% of all OC lost for these catchments. That means we are missing 90% of this terrestrial carbon. It is not there. So what are the reasons for that? One, it never got to the fjord in the first place. We're overestimating the amount actually entered the fjord. I think that's probably a good bet. Some of it might have been transported offshore through the system out to the open ocean. Or it's entered the system and then biogeochemical processes have broken it down and it's basically no longer there. Which again is a possibility. Most of these fjords are highly oxygenated and will burn through organic carbon quite quick. So yeah, my master plan to come a budget ended with this diagram, which had all this data in it, but there is 90% of the carbon for that terrestrial input is missing. So that is a thing we're constantly trying to work out what's going on. And so that was basically getting a national understanding of carbon in these systems. The next bit was to really think about how have these developed through time. So with the University of Florida, with Tom Bianchi, we came up with an idea to look at long cores. So this site, MDO42832, was a giant piston core, so 25 meters in length, which covered the last 8,000 years. We decided to look at the last millennium of basically how has human interactions in the catchment impacted carbon input. So we did all the standard things I've done over the years: measure organic carbon, measure isotopes. Tom is an organic geochemist, so we also did all the biomarkers and some metals to look at possible anthropogenic contamination. So from this plot, you can see most of the lines are fairly smooth for the first 400 years in the millennium. Then everything goes wonky, and that's when humans basically started doing their thing in the catchment. There was mining for the Napoleonic Wars, which ended up with the lead, aluminium, copper spikes in the data. There was almost complete deforestation of the catchment, and that has had quite large knock-on effects. So one of the things we tried, which was a bit novel, was we did the standard age model. We built it with shell and forearm data with radiocarbon, but then we tried to date the organic carbon, the bulk organic carbon around those dates. So the shells represent the date of sedimentation, but the carbon, the age of the carbon represents basically the age of the carbon that's or a mix of the carbon that's entered the system. So what we actually show is, again, fairly stable for the first, well, for the lower half of this core is fairly stable. There is an offset of about 500 years, so there's always this constant introduction of quite old or oldish carbon to the system. That's just the soils just basically being lost slowly during time. But when we get to the upper part of the core where humans really kick in, that age offset increases to almost 1,500 years. So the sediment is 1,500 years older than the equivalent shell at that age, which means that is very old carbon that's been eroded from the catchment. So whatever we've done at that point has basically, we've removed what we assume is trees. It's completely destabilized the soil, and all this very old carbon has rushed into the fjord. When you look at the very top, it's starting to go back to the pre-human impact stage. So again, the highland clearances maybe not great for the humanity of the west coast of Scotland, but taking the human pressure off that side of Scotland seems to have let the system recover. And we also had a go at this at the very north of Scotland. So this is Loch Erebol. We created four large cores there, and we focused in on GCO1 in the central basin, which it's muddy. And then I've not done this because I hate microscopes. We had a technician who's into pollen and has created a pollen record for this system, which shows basically a slow decline in trees over the last 5,000 years, and with shrubs and herbs taking over. And again, we tried some of this bulk dating and shell dating, and again, the offset when humans really come in jumps up massively. So this radiocarbon age, it seems to be a very good proxy for deep environmental disturbance that's basically disturbed the whole catchment. So that's good. This is still a work in progress. The last couple of things I really want to talk about is reactivity. So what I've said during this talk is that 11% of all organic carbon being buried in fjords is not true, which I don't think it is. So why are these environments still important hotspots? It's the kind of carbon they bury. So with this plot, it's quite difficult to understand, but the orange is labile, so really reactive carbon. And the blue is recalcitrant refractory, which is more unreactive to almost non-reactive. And we can see that, so in short, our fjords, there might be an estuary sample in there, but most of it is fjord samples. And we can see about 40% of the organic matter in fjords is labile. Compare that to continental shelves, where it's more like 20%. So these fjords are capturing the really fresh stuff that if it reached the outer parts of the shelf or into the coastal ocean, it would be would be broken down and release the CO2. And we can see this from this diagram. Again, it's a bit difficult to understand. the CRI is a carbon reactivity index. 1 is unreactive, 0 is fully reactive. And you can see as you move away from land, stuff becomes more and more unreactive, basically because it's been eaten and broken down by natural processes. So yeah, these fjords are storing really reactive carbon. And that's why they're important now. It's not they're storage burying so much they're way better than anything else. It's they're burying a lot, and what they are burying is highly reactive. And this is some more data to support this. This was some work done by Shui with a global data set that used a different proxy for reactivity, it used activation energy. And you can see from the very bottom panel that the fjords have lower activation energy. So it's more labile, it's more reactive than general sediments. The big error on this is because this number includes glacial sediments, which are non-reactive by nature. One last thing I want to talk about is the idea of connectivity. How are these environments connected to the wider ocean or coastal ocean? So we went out over 2 summers and collected all these samples to work out, okay, what's coming out of the fjord into the coastal ocean? How are they linked? And we did a pile of measurements, all the standard stuff, some fancier stuff at the mineral surface area, Delta 14C, to work, just to get an idea. And what we really found is, so the big panel is all the samples with that have gone through a cluster analysis, and the cluster analysis throws out 5 clusters. Red, offshore, basically sediments, largely sandy. Blue and green are transitional, and the fjords are a normal oxygenated fjord tends to come out purple, and the hypoxic ones are the orange. So that's nice that the cluster analysis threw out something that's fairly sensible. But what we really see is the fjords seem to be a largely unlinked to the carbon-wise to the coastal ocean. They seem to be holding on to the carbon that goes into them, which when we go back to where's the terrestrial carbon, we can start to sort of cross that off the possibilities that all this terrestrial carbon is pouring out of the system. Doesn't seem to be the case. So that's just one thing I'm currently working up, is this study for the West Coast. Another more global thing I'm up to is working with the group at ETH, who have basically Tim Eggleton's got his own AMS, so we could do a lot of radiocarbon dates for basically cheap. And this was some stuff I did a couple of summers ago. There's another plot, a sister plot to this, which has glaciated systems, but for this one, it's just the temperate vegetated systems. And you can see the age of the carbon in the very top 0 to 1 centimetre varies quite a lot. So the blue is Scotland. You can see there's quite a large discrepancy. So 0.7 will relate to about 3,000 to 5,000 years old. Anything above 1 is modern. And so you can see there's Norwegian stuff that's really quite old. These ones in Scotland are slight outliers. And when you look at the organic carbon content of these, you start to think, okay, did we accidentally somehow measure peat in one of these fjords? So this was Loch Etive, it's got Rannoch Moor at the top. My thought is there's some peat residue in that sample, fairly fresh, very old, that we've dated. But one of the interesting things that have dropped out of this is Iceland is almost completely modern. So all the fjords in Iceland have basically what we looking at it, the Delta 13C says it's marine, the age is very new, and the current hypothesis is the Vikings rocked up, destroyed the ecosystem, got basically all the terrestrial carbon washed away. 900 years ago, and there's nothing to actually go into these systems now. So there's no old carbon to enter the system. And lastly, there's a couple of things that I involved myself in and then suddenly in charge of. So we're currently doing a global assessment of carbon reactivity. So I asked people for samples and ended up getting 3,000 samples to measure, which is just completed. So that hopefully there'll be a new paper looking at global reactivity of fjord sediments. And one of the other things I'm starting to think about is taking the mapping techniques we used in Scotland and start to apply these to global fjords, because that's one of the big problems. We keep using just the area of fjords to do all these upscaling estimates, when as all marine scientists only sample the good sediment. We only sample mud. We never really try to get cores of sand or cores of stuff. And so these estimates are off, and we need to know by how much. I'm not saying that we'll get to a perfect number, but at least we'll get an error on it. And both these projects involve about 30 partners across all these. Some of them are fairly obvious why they're part of it, like Boulder, they're not known for having much sea, no matter fjords. But everyone here has contributed samples, data, and hopefully in the next year this will get worked up. And one last thing, I thought I'd be cheeky and advertise another seminar. So Seb Bertrand was giving a talk on glacial lake outbursts, flooding on Monday, and it's free, it's online, and go along because it's all about fjords as well. So I thought I'd throw in. And that is me. So if you have any questions, please let me know.
Excellent. Yeah. Thank you ever so much, Craig. That was a really, really fascinating talk, and I've definitely learned a lot. So I'm sure we'll have some interesting questions. We've got a few questions that have come into the chat. So first one is you show some shallow gas accumulation in subsurface sediments in Loch Sonut. Is this gas methane? How much is escaping diffusing? If methane escapes to the atmosphere, it could be offsetting the benefit of, guessing that should be carb storage.
Yeah.
Storage?
So yeah, it's definitely methane. So when we not so much Loch Sonut, Loch Etive, the hypoxic one, when we take cores, if you put lids on them, they'll blow off with the amount of methane that's in those sediments. So it's one of the areas I've currently got a project with helping with Gothenburg, who do these flux measurements. So the answer is I have no clue how much is coming out of these fjords. There's definitely methane being produced. How much? Don't know. But the Gothenburg team are coming over in May, and we're going on a cruise to try and work this out. So maybe in a year or bit's time, I'll be able to give you a better answer. But yeah, it's methane, and it's definitely being produced.
Okay, thank you. Hope that answers your question. Yeah, thank you. Do we have any other questions? Anyone want to put their hand up and speak, or enter into the chat? Well, oh, okay. Jonathan, go ahead.
Yeah, thanks, Craig. It's really, really interesting talk. It's a slightly, I don't know, controversial question, I guess. If we look at the intertidal zone that we both also work in, we're seeing the development of things like the carbon code and the salt marsh code. Is there the risk that these environments might end up going down the same route, and if so, what could be the implications?
Well, I hope not. Would be my answer. It would be extremely difficult. What I think is the carbon credits are never going to work here, which I'm thankful for. I don't need to involve myself in that. But what I would actually say is none of the carbon is, so it's not climately sequestering, right? A tree sequesters the carbon, algae sequesters the carbon, then it ends up stored here on the long term. So there's no direct connection to atmospheric carbon, really, unless something's going out. That's the only connection. So carbon credits will never work. The other side of this is marine protected areas. So do we stop this carbon being disturbed? There's a lot of really fresh carbon here. It's probably the freshest stuff in the UK marine environment. This stuff is the freshest by far, most reactive. So should we stop this being disturbed? And it's probably yes, and it's probably politically quite easy. Unlike the shelf, not much happens in these. There's people not going up and down with trawlers. One person gets caught every 10 years and gets in trouble. So banning trawling in a place that trawling doesn't happen to protect the carbon is an easy political win. And I would think that's the way they'll go. And it doesn't have to be all of them, just protect upper basins where really nothing happens and you're protecting probably 80 to 100% of the reactive carbon. It's quite an easy thing to do. And in comparison to all the other carbon schemes, protection that people are trying to do, actually protecting the upper basin of all these, most of them are unpopulated, very little going on. There's no aquaculture in the top basins. Easy in my head, but I'm not in charge of anything, so.
Great, thank you.
Thanks, Craig. I had a question. You mentioned doing a 25-meter core. Like, that just blows my mind. Like, what is the mechanics behind that?
So by some fluke, they got the Maria de France, which is one of the biggest research ships on the planet, to go into Loch Sonar.
Wow.
It had trouble turning and getting back out. But yeah, it's a giant piston core, so these things could do, in theory, 40 to 80-meter cores. So this thing didn't even get through the Holocene, so there was still another 5,000 years of Holocene below where we got that 25-meter core. So yeah, there's a lot of sediment to get through.
Definitely, yeah. Wow, impressive. Do we have any other questions from anybody? Can't see it. Yeah, Claire, go ahead.
Hi, I made it. Hi, Craig. I was just, I think it's really interesting, so thank you. I need to watch it again because I've, yeah, there's quite a lot to take in there. But it's how so I'm more interested in the subtype in the marine environment, and so looking at what proportion is coming across from the fjords into the marine environment is sort of it's I suppose it's understanding that. So it was and the lability that you were talking about as well. So the proportions. So yeah. So I'm not asking a question explicitly. I just think it you know yeah it's just we're actually really starting to get a lot better understand. We've got a lot more data now, haven't we, and stuff. So hopefully, yeah, it will become a bit clearer. But thank you.
Yeah, the reactivity of the fjords is way, way higher than anything we'll ever measure offshore.
Yeah.
I can see that Bacillus is typing a question, so if you would like to say it instead, you're more than welcome to if you want to unmute yourself.
Thank you. I am typing feverishly, but I haven't sort of formulated really a question. It was more of a comment related to the sort of conversation about blue carbon and carbon credits, is that this is far too centered on the sort of organic carbon storage. And if you've got a small sort of leakage, so these environments, these high organic carbon environments are often anoxic, where you get non-CO2 greenhouse gases being produced. And given their global warming potential, they could very easily offset any benefit of the stored organic carbon. So
Yeah.
something like 2% of the organic carbon. 2% of the organic carbon turns into methane. You're none the better, basically. You're no better off, basically.
Yeah, I agree. So a lot of this is a controversial question answer for someone who does carbon stuff is all this marine climate mitigation, engineering these systems to help climate mitigation. These systems are not supposed to save us. These systems these are the processes that have been running in these fjords for the last 11,000 years.
Yeah.
That they're not. It's that I'm more interested in that side of stuff. They're not ever going to mitigate any. They're either neutral or a source of carbon, probably in the grand scheme of things. A lot of these blue carbons things, especially when you include inorganic carbon dissolution or production. So we have to be really careful with this. Just because there's carbon there, it's connected to climate. And my real interest is understanding the processes rather than trying to link this to any sort of climate mitigation thing, because it's just not. I think the best we can hope for climate mitigation is if there's carbon there, don't disturb it. The natural processes will do what the natural processes do. If it releases methane, if it releases CO2, that's natural. We shouldn't be trying to mess that up anywhere more.
Okay, thank you, Craig. Do we have any more questions from anybody? No, I think I'll just kind of say one more comment. It was really interesting what you were saying about the kind of variability between the fjords and kind of people trying to put a global number on things when everything is quite site specific. So you need that variety of different sites to give you more context to be able to kind of have a better understanding of what is going on accurately.
Yeah. That, like, well done for them for getting a Nature paper, but that global estimate, I think there's one Alaskan core, and it's the sky high number, and that's what they use. It's like, well, that's it's a slight dodginess in there, or the errors are not reported in a way you would want. Let's put it that way.
Mm-hmm. Okay, any more questions? Or should we wrap up? 20 seconds? No? Okay, well, thank you very much, Craig. We really appreciate you giving me the talk. It was really, really interesting. Just to let everybody know, we're going to have a slight break for Christmas. So our next ECSA Files will be on the 6th of February, and it's going to be from Nathan Waltham from James Cook University, and he's going to be talking about scaling up coastal wetland restoration along Australia's Great Barrier Reef Lagoon, lessons and who will pay. So that should be really interesting. And I will let Jonathan say the final word. Oh, no.
No, just thanks everyone for attending, and see you all in 2025. And thank you, Craig.
Bye. Thank you.
Thank you.